Hello, my name is Boyan Chen. I'm currently a senior researcher from Huawei, Canada. Today I'm going to present our work towards build verifiability for Java-based systems. This is joint work with my colleagues and Professor Jianmin Jiang from York University. Build verifiability is drawing increasing attention and plays key roles in trustworthiness. Here, first we define the concept of build verifiability. If the source code under the same build process generates the exact same binary equivalent delivered packages, we consider the build process reproducible. If the delivered packages are not exactly identical, but all the non-equivalences can be explained, then we also consider the build is verifiable. That is to say, either of the above condition is met, we consider the build is verifiable. There are a lot of open source and industrial projects adopting the practices of verifiable build, such as Bitcoin, Debian, Chromium, Telegraph, Huawei, and Google. There are various benefits of verifiable build. For example, developers can know early about malicious code injection, which could prevent supply chain attack. Dependent packages do not need to be rebuilt, and dependent tasks do not need to be rerun if a rebuild of package does not yield different results. This can significantly reduce build times and lead to faster development speeds and lower costs. Regular tests are required to make sure that the software can be built reproducibly in various environments. Debian and other free software distributions require that their users must be able to build the software they distribute. Such regular tests help in avoiding fail-to-build from source bugs and can uncover rare build problems, such as timing problems, risk conditions, or builds affected by locale. Last but not least, verifiable builds plays a key role in legal requirement compliance. For C and C++ projects, there are existing practices to tackle verifiable builds problem. It is mainly achieved via three approaches shown here: controlling, remediation, and interpretation. Controlling is to first dynamically intercept build instructions and put them to a list. Then we return deterministic values, such as recorded values or predefined values, to eliminate the non-determinism. Remediation is first to identify the sources of non-determinism, manually or automatically find the problematic source code or build scripts. Then we modify the source code or to eliminate the non-determinism. Last, interpretation is to tackle certain special cases where non-equivalences are preferred, such as obfuscation. We manually inspect the rationale behind the non-equivalences and ship it along with the build packages. To tackle the issues on Java-based systems, it is a little bit different. To understand that, we first introduce the build process of typical Java-based systems. The build of a Java-based system encompasses four general phases as shown in the figure. The build of a Java application takes as input the artifacts generated by developers and produces deliverable packages that are distributed to the public. The build process is typically supported by build tools such as Maven or Gradle. The first phase is source retrieval, in which the build configuration and source code files are checked out from version management systems. The build configuration file has build customization options and a list of required dependencies. The second phase retrieves the required dependencies from package repositories such as Maven Central. A package manager resolves the versions of each required dependency and retrieves the resolved version from the repository, which are cached locally. The third phase includes compilation and linking of the cached dependencies. During compilation, one or more build artifacts called class files are generated. It is important to note that the compiler and the build tools run over the Java virtual machine, i.e. the JVM. As a result, all sources of non-determinism that affect the Java application also affect these tools. This is an important note that will be further expanded when we explain our approach to produce verifiable builds of Java-based systems. The fourth and the last phase archives all the class files generated on the previous phase together with some metadata in a delivered package. These deliverable packages are distributed as a deployable Java applications, for example, a Word file or Java library, such as a jar file. Java build tools support verifiability by offering a set of tool-specific plugins. These plugins can address three main sources of non-determinism. The first source of non-determinism is timestamps that are introduced during the build. To mitigate them, the plugins use either a controlling approach, in which timestamps are replaced by predefined values, or interpretation, in which timestamps are stripped off the generated artifacts. Another source of non-determinism is the order of files that are archived inside deliverable packages, such as jar files. The existing plugins remediate the source of non-determinism by sorting the files after the build process is finished. Finally, the third source of non-determinism stems from the metadata written in manifest files, such as usernames and tool versions. These sources of non-determinism are interpreted by plugins that strip off the variant information after the build process finishes. Although the existence of plugins is a promising direction towards build verifiability of Java-based systems, these tools still impose limitations, particularly for industrial and large-scale applications. The first limitation refers to the inability of these plugins to deal with certain sources of non-determinism, such as a non-deterministic order of the symbol table of class files. Another limitation of the existing plugins refers to the need of complex installation and configuration processes, which need to be manually repeated for each build environment. These characteristics imposes scalability challenges when adopting those plugins for build verifiability. With these challenges in mind, we have developed a new approach that is more flexible, extensible, and generalizable than the existing plugins for build verifiability of Java-based systems. In the following, we describe our approach. Our approach to achieve verifiable builds of Java-based systems comprises of 5 phases. Our end-to-end process iterates until all sources of non-determinism are diagnosed, identified, mitigated, and documented. We will first illustrate our approach with the running example. Suppose the build system has 2 source code files, bar.java and bars.java, and a Maven configuration file, pom.xml. After the build, we generate a deliverable package called full.jar, containing 2 build artifacts, bar.class and buzz.class, and 3 metadata files, manifest.md, pom.properties, and pom.xml. In the first phase, we first collect and record the build specifications and environments, such as the JDK version, the build tools, and dependencies. We then check the build verifiability by running 2 build instances on the same build specification and environment, and comparing the hash of the generated deliverable packages by the 2 build instances. If they are identical, we consider the build is verifiable and move on to phase 5. Otherwise, we move to phase 2. In phase 2, we try to identify the root cause of the non-equivalences in the 2 deliverable packages generated in phase 1. We do so by studying the existing research literature and tool documentation, and using binary visualization tools such as default scope to spot the differences between the generated deliverable artifacts. We also compare the text-based representations line by line to examine the differences. Considering our running example, After unpacking the deliverable package, 5 build artifacts are extracted. Except for POM.properties, all extracted artifacts are equivalent. By examining the differences between the generated POM.properties file by the 2 build instances, we discover that the differences regard a timestamp. The objective of the phase 3 is to leverage automated techniques to mitigate sources of non-determinism. The phase is decomposed into 2 steps. In the first step, we apply backcode instrumentation to control sources of non-determinism by dynamically altering the behavior of the build tools. As we explained earlier, modern build tools for Java systems are also implemented in Java and run over in JVM. By default, the build tools write non-determinism metadata such as timestamps into various build artifacts. To control these sources of non-determinism, we develop a technique called Java BEP environment that leverages the Java Instrument API to modify the backcode of build tools dynamically. The Java BEP environment replaces the non-deterministic methods with customized methods that have the same signatures but only return deterministic information. In the second step, we apply post-processing to interpret the sources of non-determinism. We basically apply a set of transparent rules to automatically get rid of the remaining non-determinism that cannot be eliminated by controlling. In our running example, both Java BEP environment and Java BEP fix are enabled during the build process. As a result, the timestamp generated in POM.properties files will always be the same. For each newly discovered source of non-determinism, we document its root cause and summary it into a specific category, and then come up with the mitigation guidelines. The build specifications consist of 3 parts: the build environment, the build commands, and the additional operations applied on the build artifacts for build verifiability. In our running example, we have included all the above information and delivered them to the third-party auditing agencies. Next, we introduce the case study setup. We use projects from the reproducible build central organizations as well as popular open source projects adopted in Huawei. As we can see in the left, as of September 4th, 2021, it contains 391 releases of 118 projects. Among them, there are 40 projects with 112 releases are not reproduced or verified. For the popular open source projects adopted in Huawei, there are projects like Spring, Quartz, SL4J, and so on. Here we show the quantitative results. RC means the projects from reproducible central, and CA means commercially adopted projects. As you can see, among the 46 RC projects, 42 of them can be built reproducibly with our tool. The left 4 projects can be verified as we identify the rationale of non-equivalences. And all the commercially adopted open source projects are built reproducibly with our tool. We summarize 5 root causes for the patterns of sources of non-determinism we found. For the details, please refer to our paper. Here, I'm going to just briefly discuss some representative ones here. The first root cause is the build environment that includes 4 patterns: timestamp, JDK version, Git information, and user information. Among them, the JDK version and user information are unique in Java-based systems, where the non-deterministic information are written in the manifest file. The second root cause is JDK. There are 6 patterns of them. All of them are Java specific. For example, P5, the line number table of the class files, are not generated deterministic by Java-C. The third root cause is multi-thread. P11 is about the entries that are randomly sorted. This is not Java specific, as we have observed similar issues in C and C++ projects. The fourth root cause is the other tools. For example, JSP is a Java-based technique to create dynamically generated web pages. The JSP files can be parsed to Java source code so that they can all share all the APIs and functionalities provided by JVM. To do that, we need a technique such as Tomcat Jasper. A source of non-determinism is identified during the process, as the caching option in the Jasper engine causes the generated source code have non-equivalent static variables. Both of the patterns are Java specific in this root cause. The last full cause is due to multiple reasons. This pattern occurs where there are multiple lambda expressions in the source code. When compiling with lower versions of JDK in a multi-threaded setting, the ID of the same lambda expression may be assigned in a different way. As shown here, the IDs of lambda expression of the two files are different when the two files compile in different order. And the solution is to upgrade JDK. In summary, in this paper, we first describe the definition of build verifiability and demonstrate that it is a rising concern among open source community and industry. The current approach towards verifiable build in Java-based systems have their limitations. Therefore, in this paper, we present an end-to-end solution that produces verifiable deliverable packages. The evaluation results show that all of the studied projects could achieve verifiable builds. To learn more about the details, please refer to our paper. Thank you.